Okay, we're going to get started. Thanks for joining us again for the Sustainable Phosphorus webinar series. I'm Matt Schultz with the Sustainable Phosphorus Alliance, and our topic today is phosphorus and water management on the farm. A little bit about us, the Sustainable Phosphorus Alliance. We're celebrating our 10th anniversary this year, and we're an organization that uh, advocates for the sustainable use, recovery, and recycling of phosphorus in the food system. We're supported by a cohort of members that you can see listed here and our strategic partners as well. If you'd like to support this work and the other work that the Alliance does, please contact me at phosphorusalliance.org and we can talk about getting your organization enlisted as one of our members. We don't have memberships for individual people, just for organizations, but if you're just an individual and want to follow us, we do have social media presence on LinkedIn, Blue Sky, and YouTube as well. And speaking of YouTube, we have over 80 hours of free video footage available on our YouTube channel, which is youtube.com/Sustainable Phosphorus Alliance. This presentation will be available in the coming week or two, and you'll be able to watch it again and again if you want to. In fact, if you want to take 2 weeks of vacation and watch nothing but phosphorus videos, we can help you with that. So please go ahead and subscribe to our channel. That helps us a lot, and enjoy the videos. We have 3 speakers today, and I'm going to introduce them in the order of their presentations, but a little bit of background on what the webinar is about today. Why are we thinking about water? Well, water is really the highway on which phosphorus drives. It's also, water dissolves the phosphorus that plants take up, and along with wind, it conveys phosphorus off farm fields into nearby waterways where it can become a nuisance. It makes sense then if farmers want to manage phosphorus, they need to manage the water. So today we're going to discuss some of the practices and technologies that are used to deliver water efficiently to crops, to keep the water on the field when it's needed, and to remove phosphorus from the water that leaves the field. So we're lucky to have 3 experts here to address these issues, and I'll be introducing them here. Our first speaker today is Dr. Gurbir Singh, and he's an assistant professor at the University of Missouri. His faculty appointment includes research and extension responsibilities in applied soil science, agroecology, and landscape position management. His research is focused on spatial temporal modeling of nutrient dynamics, ranging from pilot scale, or plot scale, sorry, to watershed scale. He also serves as state extension specialist for landscape position management, where his work emphasizes nutrient management for sustainable crop production that reduces environmental effects at the field and farm scale. So, Gurbir, do you want to go ahead and take charge?
Yes, thank you, Matt, and I'm audible to everyone, I hope. So
Great.
yeah, thank you. So when I was preparing this presentation, so I just had to look back into a couple of the, I think probably 10 years back of our research that we have started at the University of Missouri. At University of Missouri, we have a Grace Green Lake Conservation Showcase Farm, which is about 250 acres, where we have all these conservation practices and long-term practices, which we're actually monitoring over there. So the first question is why is phosphorus cost and loss concerning? Biggest thing is with all these geopolitical issues, and we don't have, as a US, we are actually big importer of phosphorus throughout the world, and Morocco and Russia having the more hold on phosphorus rock. So they are the big players in controlling our phosphorus prices, basically the P prices. So I was trying to make out this graph, which shows how the P prices as a fertilizer have changed over time, and that's a real input for the growers every year who are dealing with ag production. And if you see the picture of this lake, this is on our conservation showcase farm at the University of Missouri. The prominent thing in this picture you can see is all the algal bloom right around the corners. And then we are making some terraces right next to it. And for this specific lake, we have been monitoring all the inputs and outputs from this lake. The overall goal is to keep all the nutrients on farm so that we can recirculate it back to our crops when they need it. Okay. So that's the last step of any conservation practice that we can do on farm. So my research actually looks into all of these conservation practices or the BMPs, the best management practices to manage P, really on the ag lands. And once we lose this water, it's out of our hand at this point. So, a little bit of background. University of Missouri have not updated their fertilizer nutrient recommendations from almost 40-45 years. And our historical recommendations have been based off of build up and drawdown limits. Okay. If you see this first graph of the Sanborn field, where we have it's actually third longest running the rotation experiment throughout the world. And if you see these from 1880, what was the Brapey content, and then as we move through the crop rotation, basically the continuous corn that has been done for over 111 years, we actually built up a lot of P in that soil. And if you see the second graph on this slide, if you really look into that, this was one of the experiment I ran for 11 years, and where we had zero P and then a 13 P as a 13 kg per hectare of P, and then 26 kg per hectare of P applied. So where we had 26 kg of P per hectare applied, we actually maintained that soil test P value. And wherever we had the lower P, we actually had some drawdown over time. So these two graphs actually show up the built up as well as the drawdown of P. So it really takes a lot of time for P to build up and then a lot of time to draw it down as well. So basically, legacy P is a reality, and we have to address that over time with our best management practices. And the last graph shows the stratification of phosphorus in the top soil layer. So, just to cover up some background for our thinking about the phosphorus research, all in my program is basically our management practices, how we can reduce the P loss are based off of source, transport, and sink. And if you see the red boxes over here, we are doing research on all that stuff. First, we're doing research on sources where we are actually running some the field-based experiments so that we can update the soil test P recommendations for the state, so that we are not in a build-up or a maintenance kind of scenario theory. If there is a soil test P which is optimum for the crop, and we'll probably want to move into a theory that, okay, this is the maximum limit of phosphorus you can apply to your soil. Okay, so that theory has to be changed for the drawdown as well as for the built up. So that's where we are working on that. Second thing is we are looking into better P placement studies where broadcast is traditional practices, and can we move more towards a banding application of P? And then, of course, when to apply phosphorus fertilizer is always a big question. And I know because of we don't have enough resources, actually logistics to run everything so quickly in the spring. So that's why the work has to be divided. And we do a lot of transport research as well, where we have the terraces built up and we're monitoring the soil solution. And then also the last threshold that we work is on drainage water recycling. So quickly moving into some of the published work that we have published out. So this study actually we started in 2022. on already established terraces and actually it was not 2022, it was 2019. So in 2018 what happened was our that year this specific site was super wet, and all the growers that year were not able to apply the broadcast fertilizer in the fall, which is a traditional practice. So in 2019 everything got frozen, specifically in February, and that's when everyone started running their broadcast spreaders to put out P and K fertilizer on their field. So that's where we decided, okay, why not? We should actually do the same practice, business as usual, with the growers and on our research farm, and then see whether the spring applied phosphorus on the frozen soil, how much loss we can have. So for that specific study, we had three terraces where we did a surface application of phosphorus on the frozen soil in the spring, and continued this research in 2019, 2020, 2022 for 4 years actually. And then basically there are two treatments: surface broadcast P with no cover crops, and then surface broadcast P with cover crop. And in those terraces, we made out the runoff loss through the ISCO samplers. You see the picture over there. It was during the installation, and you also see the cover crop difference between the two terraces over there. Data that we collected soil test P values, we collected the cover crop and the main crop biomass as well, and then we also collected the P loss through the runoff. And if you see the rotation, one was the corn soybean rotation in a no-till scenario, and then second was corn, cereal rice, soybean, and three-way cover crop mix in a no-till scenario. So moving into our results from that specific research, the three-way cover crop mix had no effect on total phosphorus and dissolved reactive phosphorus concentrations or load in 2019 and 2021, whereas the cereal rye actually reduced the total phosphorus and ortho P load by 70 and 73% respectively compared to the no cover crop. If you see these two graphs right here, on your x-axis, you have the cost of peat fertilizer per pound, and on the y-axis is the dollars of P lost in runoff. So we actually calculate once we had measured the total P loss in the runoff water, and then we quantified the dollar value to it. So if you see the cereal rye cover crop, the yellow line over here is lower than the red line with the no cover crop is. It means, yeah, the cover crop did work, and the total loss, as the price of fertilizer goes up, and the total loss also goes up as well. And if you see the second graph is a three-way cover crop mix, we have more loss in that scenario. We also did some budgeting of P budget in this study, and again we had two treatments: cover crop and the no cover crop. And for the P budget, we use seed cost for the cover crop, and then we also made the Brave 1P before P fertilization, P applied, what was the cost of that, what was P fixed in the biomass, and total P loss in the runoff. And then we estimated the P available at basically after harvest, and then what is the Brave P at the termination, and then what was the unaccounted P for. And then doing all the math and coming up with the gross margins, whenever we had a cover crop, we had less gross margin compared to our no cover crop treatments. But at the end of the day, if we are actually treating, saying, okay, the cover crop is a better practice to manage phosphorus and keep the phosphorus on the soil within the field, then there is some losses that farmers are actually incurring in form of the yield. So to compensate for that, a cost share from this data set came out to be $41 per acre, which can actually offset the cost of cover crop establishment and then the loss in yield due to the cover crops. Okay. Moving into next, so this last experiment was just the broadcast fertilizer. Okay, then we started thinking, why not if we look into some scenarios where we compare the fertilizer which is applied on a landscape where we have a high productive soil like shoulder. A back slope can be a mid-productive area, and the foot slope is usually a lower productive area in our field conditions over here. And we now want to see that if we put this pea fertilizer broadcast versus strip till, will it make any difference for yield? Especially we are interested in the yield, and we always know if we have better incorporation of pea fertilizer rather than the surface broadcast pea, we're gonna see the differences right over there. If it's fertilizer sitting on the surface, if it rains, it's gonna run off always. If it's in the soil, it's banded at 6 inches, 7 inches. It's not exposed, so there's a better chance that it'll stay in the soil. And basically, we are building up our soil fertility bank. That's what I usually say, that it's my bank where I'm putting my money in. Okay. So the treatments were no fertilizer control, surface broadcast, and strip till band application. Let's move into the results for the corn pea fertilizer placement trial. Okay, if you look into this was run in 2023 and 2024. Our x-axis shows the years, and then the landscape positions, and then our individual treatment. NTC is our control where we did not apply any P. PB is our surface broadcast, and PST is our strip till band application. And on the y-axis, we have the corn grain yield. And if you see a thumbs up, it means that there was no significant difference between our broadcast and strip till, which means we didn't had any yield penalty. So basically, the strip till in that scenario is a better practice to manage the P application. So most of all of those combinations show a thumbs up, which means the strip till is comparable to our broadcast application, except one location which was backslope in 2023. We also measured the residual soil fertility after harvest in 2023 and 2024. That is the second graph over here. The results were non-significant, but I showed up the arrows over here just to tell you a story that there is a trend right here. Okay, so as we move from upper elevation to a lower elevation within that field, basically shoulder to back slope, the soil test phosphorus is higher. Okay, which actually tells us that there are the critical source areas which are right near on the lower slope, which usually are right next to a grass waterway or maybe a high concentrated area or high flow area. So those areas, because it's a natural slope, the soil have to move down. The dissolved nutrients have to move down. So that's why you're seeing that trend over there. Okay. If we move into our second study, soybean study, the same treatment, same everything. So in the soybean year, so all the thumbs are up, which means our strip till and broadcast, both of these treatments yielded similar. So a strip till is a better management practice for our fertilizer placement. And if we look into the soil test P for the soybean, again, there was a similar trend because as we move down the slope from shoulder to back slope to foot slope, our foot slope usually have higher soil test P values. Okay, so this gives up us into looking into more into our prescriptions. So this prescription right here covers up a lot of that we what we recommend over here in Missouri is specifically for this prescription over here. You see, it's a broad-based terrace, and all the green spots, the light green spots are the spots where we actually recommend low P applications, and the red areas are the areas which are actually higher in elevation. They are high productive areas. That's where we recommend higher P application. So basically, the variable rate technology is key for managing phosphorus. And once we have our updated fertilizer recommendations, that's when we can put up, give some recommendations for putting the thresholds that after this you should not apply phosphorus, because we want to save those critical source areas which are actually highlighted in the red dashed lines right next to those blue lines, which are actually the terrace channels, terrace creeks, from where the water is flowing out. Okay, so it's just coming back, putting all that concept together, that okay, this is the better management practice that we should do. So moving forward, what we wanted to do is we want to see that can fertilizer placement method with stacked conservation practices can improve water quality, build a soil fertility bank, and improve grain yield. Okay, and this study we started in 2023, and then it will be continued this year as well. And we had two treatments which we want to compare on a field scale. And these treatment was first was strip till, deep band plus cover crop. It was done in terraces, and it's a reduced till system. Okay, and then we wanted to compare it with our business as usual, which our growers do over here. It's surface broadcast of the phosphorus fertilizer, and then it's no cover crop with their have terraces, and then they do no-till practices. So this is our business as usual treatment. Okay, and out of these, we mired the runoff losses from these terraces and quantified the discharge. And if you really see now for these two treatments, where we had the strip till treatment with the cover crop, which is the black line, we had lower discharge because cover crops actually reduce the runoff loss, and we know that's a known fact. Whereas there's a no cover crop, we had a higher discharge. And if we have higher discharge, means we'll have higher total suspended solids, which means if there is phosphorus which is bond to the solid particles, then we'll have that higher total P loss in those watershed on those terraces. Okay. Then further, what we did was we actually quantified the event mean load for the phosphorus, and for our no cover crop, if you see, we had a significantly higher event mean phosphorus load compared to our cover crop treatments. Okay, and you see the magnitude of the difference. So where we had the cover crop treatment with a strip till, with a deep band treatment, we are actually really doing a good job on keeping that phosphorus just on that field. Okay, so in summary, the best management practice, so in field best management practice do work to reduce P runoff loss. A closer look is needed on to identify which BMPs provide a net economic benefit to the growers. Fertilizer placement is going to be the key, and then if we are doing a better management on the fertilizer placement with variable rate technology, we should be able to address a lot of those P runoff losses from the critical areas. The logistics of not being why the strip till is not being adopted is because the broadcast spreader usually covers 80 feet. Strip till usually covers 30 to 40 feet, and there's a logistics of running how many acres they can put out the fertilizer. So those things they have to be worked out really in economic form so that we can actually give the growers a better look that okay, this is more economical for you and this is not. So at the end the thing is it's just covering up all those best management practices, conservation practices, putting them into one package, and it's a tool that is available for the growers, and they can choose which best fits for their specific field. Okay. And I would like to thank you, University of Missouri's Northern Missouri Research Extension and Education Center, for allowing us to do this research, and all the research technicians and everyone who has helped in this research. Thank you.
And that was great, Kabir. Thanks so much for that presentation. I wanted to ask you one quick question, which is, did you look at dissolved reactive phosphorus specifically when you were looking at cover crops? From what I understand, uh, freeze-thaw cycles during the winter can result in higher DRP levels. Is that something that you see with cover crops? Is that just a issue of choosing the right cover crop for the right application, or can you comment a little bit about that?
Yes, we have monitored the dissolved reactive phosphorus in all of these studies, and I do agree with the freeze thaw cycles. What happens is there are higher losses of DRP. It always comes back to what is a hardy crop. If the cover crop is a cereal rye, you might see less losses compared to some other cover crops. It's the crop specific and year specific as well. So,
I see. There's a question here. Does drawdown and buildup of P in the soil take a long, or no, it says drawdown and buildup of P in the soil takes a long time relative to each other, and based on chemistry, which one is faster, drawdown or buildup?
the drawdown is going to be dependent upon your yield potential. The buildup is always going to be the long-term buildup is actually, if you see into our sandborn field and historical field, buildup can be reached very quickly. Drawdown takes more time.
Okay, great. There are a couple other questions here in the Q&A, Gerbir, but if you wouldn't mind answering those while we move on to Sandra's presentation, that would be very helpful, just
Okay.
to for time purposes. Thanks.
Thank
Uh,
you.
Thanks again for your presentation. We're going to move on to our next speaker, uh, my colleague and friend, Dr. Sandra Guzman from University of Florida, where she's an assistant professor in the Department of Agricultural and Biological Engineering. She's based at the Indian River Research and Education Center in Fort Pierce, Florida, and she leads the Smart Irrigation and Hydrology Laboratory, where her research and extension programs focus on precision irrigation, hydrological modeling, and decision support systems for specialty crop production in Florida. So, Sandra, if you want to go ahead and take over.
Yeah, sure. Please let me know if you can see my slide.
Yep, we can see it.
All right, perfect. So, hey everyone, and thank you for being here. As Matt say, my lab focus on smart irrigation and hydrology. But today I want to talk more beyond the word irrigation because, as Matt mentioned, every time we make a water management decision, we are also making a nutrient management decision in the field. And this is what my talk is going to be about. By the end, I want you to think about technology, precision irrigation, precision farm management with a different perspective and how we can utilize these tools for management. So we are moving from agronomy prescription from the first talk of nutrients to nutrient management in general. Let me start by clearing up something that usually gets confused. What is a smart irrigation or what is a smart ag? and what is precision irrigation. They are not the same thing, even if they are related. Smart irrigation is about automation, so how we use controllers, how we use apps, how we use real-time data, how we use information for management, and then we make a manual decision. We can have our system. The farmers, the growers, can have their own management and make their own decisions based on what the data is saying. When we talk about precision irrigation, we are going further. We are responding to the variability in the soils, in the soil nutrients, and how the soils vary. Plant variability. In my case, I work mostly with specialty crops, fruits, and vegetables. So we will have in tree crop systems different plantings and different phenological stages in the same field, and also the weather part. So if we have a high intensity rain versus a lower intensity rain, how we can move from those kind of things. So smart irrigation and precision irrigation use kind of the same set of tools. When we are talking about precision irrigation, we are getting into the field of automation. So, for example, in this farm that you see over here in this image, we have different soil types, 49, 6, 56, and 38. So we have 3 or 4 different soil types. With the smart irrigation, we can make a decision and weigh the pros and cons of irrigating or managing fertilizers based on the on soil number 38, which is the majority of the soil. With precision irrigation, we will have and we will be able to make assessments based on the 4 different soil types. The same with water. The only valve for this particular farm is located here. So we have one source of water. With smart irrigation, we make the decision, and using data, we have information about a volume that applies for all soil types. Then with precision, we will have variable rate irrigation. The same with fertilizer, we will have the concept of variable rate fertilizer. So fertilizers for this soil, different for this soil and this other soil, right? Soil moisture sensors in general are of the precision irrigation technologies, one of the most used technologies right now available for in the entire country, and the most popular precision management tool that we have for management of irrigation. So soil moisture sensors are in between. They can be smart, and they can work with precision irrigation as well. These sensors are already in many fields. There are subsidies and programs that encourage the use of these sensors in the field. However, most of the growers don't realize that these sensors have time series and data more that goes further than water management. So what else a soil moisture sensor can do? So soil moisture sensor measure volumetric water content, or how much water is in the soil, and also measures EC, or electrical conductivity, which tell us how many dissolved ions are in the water. In addition, we have metrics of soil temperature as well from these sensors that are already installed in the field. So when fertilizers dissolve in soil water, they add ions, and the electrical conductivity goes up. So the same sensor growers use to schedule irrigation can also pick up a signal every time nutrients are dissolving and moving through the soil. And that connection is what it brings the soil lab testing and the soil management in the field. So now, if sensors can track nutrients continuously, why we are not using them already for nutrient management? Um, Most nutrient management decisions should be based on lab analysis, right? So the lab analysis, taking a core sample of the soil and sending the lab analysis will give information about the total nutrient pool that is in a particular field in a moment of time. This is kind of a snapshot of what is going on with the nutrients in the soil before planting a crop and before doing any management. Now, the blind spot is that over here we know what is in the soil at the particular moment that the sample was collected. And this gives us information about the concentration of nutrients that are in the soil prior to any fertilizer management practice. This information, the one that is sent to the lab, is extremely important to assess the nutrient management per crop per season. But there is no visibility here on how those nutrients are moving or how fast those nutrients are moving when it rains or when we have irrigation. And that is a gap that is related to this snapshot versus real-time movement analysis. So to understand how sensors can fill that gap, it's important to first understand what drives nutrient movement. And again, you will hear this multiple times. The relationship between water and how we manage water and nutrients together is actually very important. So too little water. When we have too little water, fertilizers that they don't dissolve, they stay there, they stay put, and then the plant cannot access it. It will stay in the soil. When we have the right irrigation, then the nutrients will reach out to the root zone, and the plant will take the nutrients up. When we move to too much water, then the nutrients will dissolve and move past the root zone into the groundwater and eventually into freshwater systems through leachate. Every irrigation decision is also a nutrient fate decision, and this is kind of the main driving question from our team research. So the study that I'm going to show you here, the main question we got was if electrical conductivity responds when fertilizer dissolves and move, can we actually use that signal to track where nutrients went in real time? Can the same sensors that we use to schedule irrigation also serve as an early warning system for nutrient leaching? So our STEPS Science and Technologies for Phosphorus Sustainability former master scholar, Daniel Palacios, tested this as part of his master thesis. And we found that the answer was yes, but with some important conditions and caveats. So we set up a control experiment at the Indian River Research and Education Center here in Southeast Florida. We had soil columns, multiple soil columns, more than 12 columns filled with clean sand, so no prior fertilizer applied, 3 irrigation volumes, and 4 fertilizer rates. We define the irrigation volumes and fertilizer rates for citrus trees based on the University of Florida citrus water and nutrient recommendations. We put 2 soil moisture sensors at different depths, at 40 centimeters from the bottom of the core and 25 centimeters from the bottom of the core, and did a destructive sample every week after simulating different irrigation pulses and different volumes, and sent those samples to the lab to assess nutrient nitrogen, total candidate nitrogen in this particular case. We also work with phosphorus, but we got that the concentration information from the lab. So we had both the continuous sensor data and point in time lab results to make a comparison. So we make a comparison of the snapshot method versus the continuous method side to side to see how well they agree. Some of the findings we got from this study, the first finding was that electrical conductivity actually had a significant response to fertilizer rate with high significance. But only the highest rate, which was 2 times the University of Florida recommendation, was the one that produced a signal clearly distinguishable from the control. At the normal or half nutrient rates, the sensor couldn't tell the difference. So I like to explain this result as when we have a coffee cup, when we are drinking coffee and we are dissolving sugar in coffee, we will need to have enough sugar before tasting it, right? So that is the concentration threshold that the sensor need to cross before it responds, that tasting like kind of threshold. And this is important context for giving interpretation of how the sensor data works and the need for higher sensitivity in precision nutrient and water management. We are focusing on electrical conductivity particularly because electrical conductivity is the main variable that drives irrigation, not only irrigation, but also fertilizer management. So if you see those images coming from the drones and these field-based nutrient phosphorus use efficiency assessments from satellite image or from drones, the main driving parameter is electrical conductivity. The second finding we got was that we were able to have an idea of how the nutrients were moving from the upper layers of the soil to the deeper layers of the soil. I want to be very clear with this study because sometimes it gets confused. We are not talking about phosphorus concentration or how much phosphorus is available in the soil. We are talking about how we can track the movement of nutrients or salts across the soil profile. So in this case, the deeper sensors consistently show 18 to 22% higher electrical conductivity than the shallower sensors were when the water was moving. So that gives us a strong indication that the nutrients were moving downward through the soil profile. So a rising electrical conductivity signal, as you see here, in the upper sensor is telling us that the nutrients are in the upper soil layers. As we put water, they start moving through the deeper sensor, and that is what is giving us the early warning system where we can see and we can have an idea of where the nutrients are living, the root zone, if irrigation was too high or we have high volumes of rain even getting into the field. So this is kind of the leaching signal. We can see this information in real time. And use this information as complementary to the lab analysis that are being sent to the lab. This last slide of the studies kind of brings everything together. So overall, the electrical conductivity and lab nitrogen data did not correlate. Did not have like a good correlation, and this was expected because we were not focused, and we are not using the sensors to assess concentration of nutrients. However, a really good point over here is that with medium water, with an optimal irrigation management, actually we saw one strong correlation between electrical conductivity and movement of nutrients. And why this is happening? Because a low irrigation volume, the fertilizers didn't dissolve enough to produce a detectable electrical conductivity signal. At high irrigation, the nutrients actually leach too fast, passing the sensor before the sensor could make register any information about electrical conductivity. So at medium irrigation or at optimal irrigation, this is kind of the Goldilocks kind of volume. There was just enough water to mobilize the nutrients into solution without flushing them away. The sensor and the lab had agreement, the lab sampling and the control have a really good agreement for medium water for the optimal water application, and confirm to the main hypothesis that we have and what I was showing in one of the first slides that I present, that the irrigation volume you select and you work with actually have a direct impact in whether the sensors can track nutrients, but most importantly, whether the nutrients are staying in the root zone or they are just being washed away through leaching. And here's what kind of the sensor data looks like in. Give me a second, please. Okay, I cannot. Can you still hear me? I'm not entirely
I
sure.
can hear
The
you,
video.
Sandra. We're not hearing anything
Okay.
from the presentation. Yeah.
Okay, good. Thank you. I appreciate that. So here's what in practice it looks to have data for irrigation for smart irrigation management. This is a snapshot and a demo of Irrig Monitor. Irrig Monitor is a data visualization tool that we develop in our lab that includes Internet of Things, and we have also the human in the loop component, like farmers' decisions incorporated in the system, and soil moisture forecasting for irrigation management. What you see over here is real-time sensor data coming from two depths. So on the left side, you can see topsoil moisture, bottom soil moisture. The colors represent good, medium, and high water availability, even above saturation. So in the upper sensor, we have 16% moisture, good moisture for sandy soils in Florida. And in the bottom sensor, we have 29%, very high. So we have higher moisture in the lower sensor than in the upper sensor. This is a snapshot from a field, from a citrus field here. So it's real information. When you see, you also have information about in the upper part, right side of soil water content and electrical conductivity. And you can see that when there are increases in the soil water content, we have also spikes in electrical conductivity. So when you see the deeper sensor or the lower sensors, electrical conductivity moving up, while the shallow sensor is just flat, is plateau. That means that there is a leaching signal, and we can have that as an early warning system. You will not need a lab result to see this. Actually, if you have access to this information, you will see right away that electrical conductivity was rising below the root depth for over and manage your irrigation. So this system connects all of the information available, including weather forecast, including rain forecast, and it gives a recommendation to the farmers on how much to irrigate and what is the optimal irrigation management. So at the end, if we manage irrigation if we optimize irrigation management, then we will have better management of fertilizers of the fertilizers that are being applied into the soil. And finally, I just want to like close up with things that we have discussed today in my talk. We talk about the difference between smart and precision irrigation. I hope you got the difference, and if you have any questions. We also learn or discuss that soil moisture sensors can also measure electrical conductivity, and that the signal actually responds to dissolved nutrients or salts in the soil. Um, we can see that water is the vehicle that moves nutrients, and that irrigation nutrient volume determines whether those nutrients stay in the root zone or they leave. And finally, as a main reminder, smart irrigation is not longer about just saving water. It's actually about keeping the nutrients where the plant can use them. Um, this work connects to the work that we are doing at STEPS, the Science and Technologies for Phosphorus Sustainability Center, where my team is part of a broader effort to reduce phosphorus losses to water by 25 in 25 years, 25%. Water and nutrients are kind of married, are together, and the sensors can show that. And with that, I will stop in here.
Okay, great. Thank you, Sandra, so much for that presentation. We just had one question, although if others want to ask questions, feel free to add those to the Q&A box, and Sandra can answer those afterwards during the next talk. But Sandra, the question that is here is really about the placement of the sensors, and so in relation to the root zone. So where is the shallow and the deep sensor with respect to the roots?
Oh, that's an excellent question. I appreciate it. I can give clarification. So, the shallow sensor is usually when we have two sensors. The shallow sensor is usually installed in the effective root depth of the crop, and the deeper sensor is installed way below. So the upper sensor, the shallow sensor, is used for irrigation and nutrient management, and the deeper sensor is to assess leachates, so nutrients and water that are leaving the effective root zone.
Okay, great. And then a second question was whether you've investigated correlations between electrical conductivity and P soil index.
Yes, we did. We did an assessment for nitrogen and for phosphorus separately. The assessment for phosphorus actually uh, gave us gave us information where because phosphorus moves with water as well, but the movement is slower. So we are working right now on data analysis tools to increase the weak signal that we are getting from phosphorus, so we can have better data displays when people are using irrigation management tools, precision irrigation management tools.
Okay, great. And one more question, then we'll get on to the next presentation. Is dilution accounted for in the EC signal?
Ooh, that's a really good question, and I I can say yes and no. I don't think that's the complete. I can say like yes or no, but when the dilution happen, the signal just get weaker, basically. So that's kind of the way that we can infer the movement of ions, but not directly. That will be indirectly.
Okay, great. And thanks again for your presentation. Um, we're going to go on now and move to our last presentation. which is from Dr. Vinayak Shedekar from Ohio State University, where he's an assistant professor of agricultural water management in the Department of Food, Agricultural, and Biological Engineering. And he also directs the International Program for Water Management in Agriculture and the Overholt Drainage Education and Research Program. His research and extension work focus on agricultural water management, water quality, and soil health to advance sustainable and resilient farming systems. He's also lead organizer of the annual Overholt Drainage School and administers the process for the International Drainage Hall of Fame. And I'll let you go ahead and take over then, Vinayak.
Thank you, Matt, for that introduction. Really appreciate the invitation to speak here. I'm going to turn off my video. Just wanted to make sure I at least am visible for a few seconds before I start sharing my slides. Can you confirm if you can
we can see
my
it.
slide?
Okay. Yep. Great. Thank you.
Okay. Thank you again. And as I said, I am really glad we're talking about phosphorus in three different contexts. And I guess today I'm going to talk mainly in the context of drainage and drained landscapes as it relates to phosphorus. Just wanted to share a few initial thoughts on the background with respect to drainage. My colleague Zaysan is on this webinar already, and these are images from some of his work. Subsurface drainage and surface drainage are the two main forms by which we tend to remove excess water from landscapes, especially where we need it. Drainage is kind of a global practice, if you will, very similar to the adoption of irrigation. There are certain areas where drainage is much needed. If you look at the entire world, about 14% of the cropland is drained. Look at US, about 37% of our cropland is drained. I'm from Ohio, so in Ohio, we estimate that about 3 to 4 million acres is drained. So it's a significantly large amount of acreage that is actually has seen some kind of drainage. Especially if you look at the Midwestern landscape, we tend to have some of the world's most intensively drained cropland. And there are a couple reasons why we have that. Number one is a majority of the Midwest is kind of a water-rich region. They receive about, depending upon where you are at, anywhere between 30 to 40 inches of rain precipitation in a year. But the unique thing about that precipitation is about half of that precipitation comes during the very cold and non-cold part of the year when we are not growing crops, and that water tends to not evaporate and tends to linger on that landscape. So we have too much water. To make things worse, the Midwestern landscape is also characterized by what we call poorly drained soils. You put those two together and you get the recipe of waterlogging and poor trafficability. And hence, we need drainage in those landscapes to be able to sustain crop production. So I like to say that the drainage is very essential for crop production in the Midwest. And the good news is over the years, the way drainage, the practice of drainage and the theory of drainage has evolved. We tend to design these systems to optimize the objective function that is the trafficability and the crop growth. Any intensive drainage beyond that is basically additional investment that you are putting in that may or may not be needed. So it's important to kind of think about that golden rule of drainage when it comes to that practice. Today, we're talking about some of the potential side effects. As I said, it's an essential practice, but are there side effects? Yes. We now in the last decade or so have started seeing more intensification of drainage. But then drainage kind of creates a direct pathway or a short circuit pathway for the water to reach the downstream water bodies and hence carry some of the nutrients with it. We will also talk about some of the ways we want to minimize those impacts as well. Matt, if you don't mind, give me a 5-minute warning during my presentation. I would appreciate that. So most of you are aware of the role that drainage would play in terms of moving these nutrients or excess nutrients from agricultural landscapes wherever agricultural drainage exists. One of those is nitrogen that can essentially leach out of the soils and move with the drainage water. This is not necessarily a Ohio context, but wherever you have freshwater bodies, phosphorus also becomes an important nutrient that is being lost from these landscapes and finds its way into the freshwater bodies, which lead to the harmful algal blooms in those water bodies. And here is the little image of Lake Erie. Over the last couple of decades, Lake Erie has experienced different severity of harmful algal blooms, and there is a direct connection between how much phosphorus load comes into the lake and the severity of that bloom. So the idea was to kind of aim for minimizing that severity based on all of the severity assessments. That led to Ohio's Domestic Action Plan as well as the Great Lakes Water Quality Initiative that put some target reductions for phosphorus loading coming into these Great Lakes, especially for Lake Erie. We are looking at about 40% of the base load of phosphorus we had in 2008. And that goal is for the Western Lake Erie Basin as well as individual rivers that actually lead into the lake. That target is not only an annual target, but also a seasonal target where it's March through July loading. So if you take this reduction that is expected out of the entire watershed that is leading into the Lake Erie and divide it over the landscape, you're looking at about half a pound of total phosphorus reduction from those landscapes per acre, and then about 0.14 to 0.08 pounds of dissolved phosphorus loss reduction across that landscape, which is kind of an interesting challenge to look at. Something unique that happens in terms of the phosphorus that drives these blooms is the dissolved part of that phosphorus does move with the water. It's a very small fraction, but a majority of the phosphorus actually is attached to soil particles. So there is a very close relationship between the total sediment loss and total phosphorus transport from these landscapes. So runoff and erosion processes become important, but then as far as the algal bloom severity is concerned, the leaching of dissolved phosphorus also becomes important. Something unique for especially Lake Erie, this is just the Maumee River Basin within Lake Erie, but the brown part that you see in this pie chart is amount of total phosphorus or total nitrogen loading that can be attributed to non-point sources. And as you know, agriculture is one of those non-point sources. Of course, there are point sources that are highly regulated, but the bigger challenge is to be able to kind of control the nutrient losses from especially watersheds that are heavily agricultural watersheds like the Lake Erie Basin. Just to give you some reference point, about 70% of the cropland in the Lake Erie Basin is agricultural land. So you can imagine how large a contribution it might have, even if with a small amount of phosphorus loss. And when it comes to phosphorus loss in any landscape, I think you're looking at two things: source, in case of agriculture, that is nutrient application or whatever soil phosphorus that is built in that landscape. But then you have to have a transport pathway with respect to that phosphorus being lost from that field. So we're going to switch gears and look at kind of try to understand the phosphorus loss, especially from the drained landscapes. Many of you are very well aware of the general pathways through which phosphorus could be lost. In the absence of a subsurface drainage system, you're only looking at surface pathways and some seepage losses as a source of phosphorus into the receiving water bodies. But as I said, as soon as you introduce drainage, you are looking at some of the preferential pathways that may be connected with those drainage systems, as well as some of the soil matrix flow that might contribute that phosphorus in those short circuit pathways. So I wanted to give a kind of a bird's eye view in terms of what is known so far in the as it relates to drainage and phosphorus loss. I found this really outstanding paper by Dr. Laura Christensen. Looks at over 50 years of studies with respect to drainage and phosphorus loss. Um, the interesting thing to notice here is only they estimated that only 2% of the applied phosphorus is actually lost in drainage waters, which really continues to just amaze me because it's such a small amount of phosphorus that is being lost. Another thing to notice here is this box plot that you see is basically uh, dissolved phosphorus and total phosphorus loss in surface waters versus drainage waters. And what you see is drainage water actually leads to a very small amount of phosphorus loss compared to what you might see from a surface runoff pathway. The rest of the data is a lot of it comes from Ohio. In Ohio, and many of my colleagues across Midwest rely on what we call edge of field monitoring of hydrology and water quality, where we instrument sites for subsurface drainage outlets as well as some of the surface runoff pathways. And we use very continuous monitoring techniques, high resolution sampling techniques to be able to answer these questions. So Dr. Kevin King and the Soil Drainage Research Unit here in Columbus has a network of sites. I have some sites that contribute to that network. But we're looking at about somewhere between 400 and 800 years of site years of data. This is only based on 200 site years of data. Every dot that you see here in on the map of Ohio is a paired research site that contributed that data. In general, as I said, we get about 40 inches of rain. More than half of that rainfall or precipitation is lost to the atmosphere in the form of evapotranspiration, which leaves about like other half for water to transport either over land or below the land surface. If you look at the proportioning of pathways of water that is being lost from the landscape, you can see about 30% of the precipitation, especially in Ohio, is lost in the form of style drainage or drainage discharge. Only 6% of that precipitation is lost in the form of surface runoff. We have many sites where we observe almost no runoff, but we consistently tend to observe about 11 to 15 inches of subsurface drainage discharge in a year from these sites. Which kind of leads to the conclusion that subsurface drainage is the major pathway or hydrologic pathway for water loss from these croplands that are drained. If you take that and apply the concentration data to the discharge data, then you're looking at nitrate losses in pounds per acre. You can see the light bars here are subsurface drainage pathway losses of nitrate, and then the dark bars that are appearing in some sites. And these are all those 40 sites that that Dr. King has monitored over years. And this is kind of an annual loss per acre that you're looking at. And you can see that subsurface drainage is the major pathway for nitrate loss. Anywhere between 10 to 100 pounds of nitrogen being lost in any given year, which is really large, very wide range of nitrate losses from these landscapes. But as I said, the drainage tends to be the dominant pathway for nitrate losses. Very similar trend for dissolved phosphorus losses, but the magnitude is several folds smaller. As you can see, it's about less than a tenth of a pound of phosphorus per acre being lost to about a pound or pound and a half of phosphorus being lost through these subsurface or surface drainage pathways. And again, subsurface drainage does tend to be a little bit on the higher end for being the major pathway for phosphorus. So to put it all together, the conclusions that Dr. King always likes to share is about there are several fuels, agricultural fuels. If you were to put that criteria from the Lake Erie phosphorus reduction goals, that would actually violate that criteria and are exporting above that the threshold that was set for the reduction. That's where we have the need for conservation practice implementation. But then this is very important to note that about 70 to 90% of the excess nutrient loss is coming from the drainage pathways. So you can imagine how important it is for us to think about drainage water management as a way to kind of mitigate these nutrient losses. Now, there are some other conclusions that have come up as these studies have gone on. One conclusion was, in general, if you have very high soil phosphorus in these drained soils, that kind of relates to a little bit of a higher risk of phosphorus loss from those fields. But just higher STP doesn't equal higher environmental risk for phosphorus loss. We do see some sites that are exporting very small amount of phosphorus, even if they have high soil phosphorus, very site-specific characteristic. Another thing that Dr. Will Osterholz has concluded was where is this phosphorus coming from? Is it coming from fresh phosphorus applications like fertilizer or manure? Or is it the phosphorus that has built as a legacy in the soils? And the answer is it's actually a lot of the phosphorus that is coming into these tile drainage systems is coming from the legacy of phosphorus that is built. So it's a long-term problem to solve, and drawdown is not the only solution or not an easy solution for minimizing the risk of phosphorus loss. Another conclusion, which is complicated, but I'll just state the fact that 20% of the highest precipitation that occurs in a year carries up to 40% or 60 to 70% of these hydrologic or nutrient losses. In other words, extreme precipitation events drive a majority of nutrient losses, and that is true for phosphorus as well as nitrogen. And it's very well known. This is where the opportunity is from the mitigation standpoint, is that maybe there is a potential for us to think about managing that water, especially during those extreme events, to be able to minimize the losses of phosphorus. There is another context that I have not talked about at all, and I really like talking about, is the other risk we have for the crop production in the Midwest. The fact that we are experiencing drier and hotter summers and will experience in the future is going to drive some of the discussion on water management, and I'm happy to discuss that at a later point of time. I wanted to spend the last couple minutes on some of the mitigation techniques. Matt, how am I doing on time?
You're doing fine, Vinay.
Okay, thank you. So I went through a lot of slides, and the idea is, I think the take-home message from those slides was the fact that drainage tends to be the major pathway for nutrient loss. Hence, any mitigation strategy you're going to think about has to have something to do with drainage and water. So, of course, there are many other practices, as Gurbir brought up, that start in the field, within field, that are agronomic practices, and they are very, very effective practices when it comes to mitigating nutrient losses. Context that I'm going to talk about is very much driven by drainage and water management. So I'm not necessarily saying that this is the only list of practices, but I want to talk about these practices and their importance in this whole equation. As I think Dr. Kevin King always says, there is no silver bullet when it comes to solving these problems, and which is, I think, a very important realization that we have to have. But when it comes to practices that can help us manage these water quality issues or in the drained landscapes, here is a kind of a running list: controlled drainage, blind inlets that can treat some of that high phosphorus concentration, drainage water recycling, where you're essentially storing and recycling the drainage water. Cover crop pops up as even a water management strategy, and I'm not going to talk about it, but wetlands also become an important part of that piece. There is many other practices you can list on this list. But I want to focus on controlled drainage or drainage water management. Essentially, instead of letting a drainage system freely drain into your waterways, it's very easy to put a dam on that outlet, especially when you don't need drainage, such as winter time when we are not growing crops. We could raise the water level in that field, kind of return that landscape to be an undrained landscape. Springtime, when we need to plant, we can drain the landscape. Summertime, there is opportunity for us to retain some more water in that soil profile for peak demand season. And then again, during fall or harvest time, we could lower the water table. So there is a way that you could manage drainage systems for a specific outcome. In this case, this retention that you achieve in the winter time is the kind of the bigger factor that will help us with nutrient loss reduction. And there is plenty of studies that have been conducted over the years. This is a regional synthesis that was done for controlled drainage as a practice across the Midwest. All of these dots are research studies. And it shows that there is a range of reduction that you will see in drainage outflow and hence associated nitrate loss reduction, up to 50% nitrate loss reduction or discharge reduction. Unfortunately, when we started synthesizing these studies, there was not a lot of data on phosphorus loss. So at least this synthesis concluded that we can't comment on phosphorus loss, but there is potential for controlled drainage to actually help reduce phosphorus loss. Of course, I talked about agronomic benefit of retaining that water to crop production with controlled drainage. There is only a handful of studies that actually look at controlled drainage and phosphorus loss. One of those studies is by Dr. Kevin King. Again, I'm part of that study. And essentially, he had two paired sites where they tested controlled drainage. At one site, we saw some reduction in the edge of field phosphorus loss. One site, not so much. So essentially the conclusion here is controlled drainage does have the potential to also rise up as a practice to reduce phosphorus at the edge of the field, but we are now seeing the need for this practice to be managed strategically or paired with another practice that will actually enhance the phosphorus reduction at the edge of the field. The bigger picture for this practice is I still very much support this practice for the landscape of Midwest. The reason is it's already a win-win practice from crop production and nitrate loss perspective. So that's one way of looking at it. The other way of looking at it is whether or not farmers are really going to be able to use this practice. It's very cumbersome when it comes to managing these control structures. Typical farmer has to go out there at least 4 times a year and pretty much wrestle with these structures. So there is a newer opportunity with what we call smart drainage systems, where instead of these individual boards sliding up and down, there is a automated system that is controlling a valve and actuating that valve in response to the water level that it is seeing in the control structure. And you can have the controller be scheduled in a way that it is managing those waters for crop growing season versus non-growing season in different ways. And you can set different set points higher or lower so that that valve is automatically managing that water level in the control structure. And this presents a kind of a very newer approach for managing controlled drainage systems. And I'm very hopeful that this might actually become a very good way of managing for phosphorus, because active management tends to be the solution on maximizing the phosphorus loss reduction. I'm going to simply indicate here that during growing season, this practice has the ability to store about 1 to 2 inches of water in the soil profile. Again, Hassan is on this call and he has done some research with phosphorus and controlled drainage. And as a community, we are still exploring the promise that this practice provides for phosphorus loss reduction. On the Another possibility with controlled drainage is that you could then use it to pump water back through the drainage systems, and pretty much I like to call it reverse drainage, but essentially facilitating what we call a sub-irrigation system. Not going to talk about that much, but also that is the advantage of this. The last practice I want to talk about is drainage water recycling. There is again a regional synthesis of this practice that was done, and there is a potential to reduce the nitrogen as well as phosphorus losses by up to 40% if we are able to retain and recycle some of the drainage water, especially in the Midwestern landscapes. I want to show you some example data from my site that we have established in 2024 at Ohio State University's Lima campus, where we are essentially collecting drainage water from drained landscape and recycling that back using a center pivot system. And then the first advantage of that is just because that water is sitting in the pond for a long time, it has tremendous potential for actually lowering the concentration of nitrogen as well as phosphorus between the inflows and the outflows. So that is the co-benefit of having the pond there to treat that water just because you have retained the water. The other opportunity we have is a strategic management of the stage in that pond and creating storage ahead of extreme events. We have actually demonstrated last year that you could create a very much like a zero discharge system by storing the water from high risk events. And that is another new concept that we're thinking about that is possible if you are automating and using smart systems to manage these ponds. As I said, managing for those extreme events is going to pay dividend on maximizing the nutrient load reduction. So the goal with drainage water recycling, this is not a new concept. There is irrigation tailwater recovery as you go to some of the other states in the southern or western United States. It's not a new concept. What is new is timing of the management and retention. So I want to conclude by basically expressing the importance of water management in these drained landscapes. I do think that the retention and recycling of water, especially drainage water, is going to be the future because it's going to be a win-win situation. One way to do that is going to be stacking the smart drainage technology, the controlled drainage technology, and some of the treatment options in this whole at the edge of the fields to maximize the benefits. So I'm going to stay on this slide. I showed you the golden rule of drainage. This is what I think a majority of us in the Midwest as experts are agreeing to is yes, that the golden rule of drainage can be modified further to highlight the importance of storing and recycling of the water. So I'll stop there, Matt, and
Great. Yeah,
take any questions there may be.
yeah, thanks so much for the presentation. It was excellent. And we did have some questions. I think we have time for one or two here. One I would like to address is this one about hot moments. And so you talked about, flashy storms delivering a lot of delivering a lot of nutrients or conveying a lot of nutrients. And is there evidence that a relatively small number of fields also contribute a disproportionate share of nutrient losses? So they're kind of asking, you have this temporal aspect of flashy storms and these certain events, but there are also a spatial component where there are just hot spots in terms of the landscape that are releasing more nutrients. And then how do you target those specific fields?
And I'm glad you asked that question. There is actually Ohio has what we call a H2 Ohio program, which is driven by essentially incentivizing water quality mitigation across the Northwest Ohio, especially for Lake Erie. And they recently released a program that is focused on legacy of phosphorus or these hot spots. One of the challenges is the hot spots do exist where you might have had historically high phosphorus application either through a continuous manure application or just naturally occurring high phosphorus concentration in the soils. Some of the work that Dr. J. Martin's group has done here in OSU at OSU concluded that the hotspots are not like an entire field being a hotspot. We have 40 to 60 acre or 100-acre fields. You may have a hotspot that looks more like 2 or 4 acres. We have done some special research that is focused on those hotspots, and what we're seeing is with even those smaller hotspots, like single hotspot within field, does increase the risk of higher phosphorus concentrations being in the drainage water. How do you identify those fuels is a very difficult question to answer depending upon which state you are in, mainly because the data exists with farmers and not with the agencies. Dr. Martin's group has been very successful by creating what they call a public-private partnership, where they have relied on the nutrient service providers to be kind of the mediator between connection for like a farmer that we can identify to implement a more targeted practice. However, the ODA's assessment, Dr. Kevin King's assessment, and Dr. Martin's assessment all show that it's a very small fraction of total acreage that has these hotspots, but it does have a disproportionate share in the phosphorus export. So it may be somewhere between 3 to 5% of the hotspots landscape is exporting maybe 10 to 15% of the phosphorus overall. Don't take these numbers as the final numbers, but that's what I remember. So there is a bit of a disproportionality, but there is also a practical challenge with respect to being able to find those fuels and then apply a practice that would actually work for reducing that phosphorus loss. Sorry, I
Great.
give you a longer answer, but yeah.
No, that's fine. Folks, we have a lot of questions here, a lot of good questions that unfortunately we're not going to have time to get to, but maybe we can leave with this last one. I'm going to try to bundle some of these, Vinayak, and they're about the economics of drainage water recycling. And you're taking land out of production. Have you looked much at that?
Yes, there is a report by ISG, Environmental Working Group, Defense Fund, and Chris Hayes, one of the authors on that. And they have looked into the economics. We do see the economic benefit, but taking land out of production is a major concern. And there are ways you can optimize these systems by shrinking the size of the pond. So yes, there is a whole science behind being able to optimize the design. Transformingdrainage.org is a good website to go to. And then again, as I mentioned, there is a economic considerations report by ISG that recently came out, and I'm happy to share that for the mailing list that you may have here. So that also talks about that economics. Not
Great, thanks,
easy,
Vinayak.
not
Maybe I can
easy to
put
adopt
those.
that practice.
Yeah, sorry. If you send me that, I'll try to put it in the notes for the recording that we put up on YouTube. I want to thank all of our speakers again for their contributions today, and thank you all for coming to this event. We'll have another webinar at the end of August on critical minerals, so I hope you come and join us for that. Thanks, everyone.